This is Pre-Calc, section 3.7, part 2. In part 1, we were taking zeros and coming up with the function. In this part, we're going to have the function and we're going to find the zeros. But first, there's a couple theorems that you should be familiar with. One is the fundamental theorem of algebra, and it's this. Every function defined by a polynomial of degree 1 or more has at least one complex zero. Now, complex zeros include real zeros. A polynomial function can have only real zeros, or only complex zeros, or both real and complex. So here's a couple examples. Function x cubed plus 2x squared minus 3x, it has three real zeros, and they are -3, 1, and 0. These are rational zeros. These are real zeros. Now you can verify all of these by plugging them in the calculator and taking a look at the graph. If you put this in the graph as y equals, you will see your graph cross at these three places, -3, 1, and 0. Another possibility is this x to the fourth plus 13x squared plus 36. It has four complex zeros. Same deal, you can put it in the calculator and you will see it does not cross the axis at all. And the reason it doesn't cross is because it has imaginary roots of plus or minus 2i and plus or minus 3i. And you might wonder, well, how do you know that these are the roots? Well, this happens to factor as x squared plus 9 times x squared plus 4. Set it equal to 0 to solve. Set each one equal to 0 and solve. X squared plus 9 equals 0. The only way to solve this is to subtract 9 from both sides. Take the square root, and there is your imaginary plus or minus 3i. And the same thing's going to happen over here with x squared plus 4. The other possibility is something like this, x cubed minus 3x squared plus 4x minus 12. It actually has one real zero at 3, and it has two complex zeros of plus or minus 2y. This, if you plug it in the calculator, you will see it cross at 3. And a little bit later on, I'm going to show you what you do with that real zero of 3 to come up with these two complex roots. That's coming up. Another theorem that's important is the number of zeros theorem, and it's this. A function defined by a polynomial of degree n has at most n distinct complex zeros. So y cubed has at most 3 complex zeros. Y to the fourth has at most 4 complex zeros. So we start with this. We have this polynomial right here, and you're given the fact that 5 is one of the zeros, and you're asked to find all the remaining zeros. This is something that we did in college algebra. What you want to do is take that 5 that you were given and do synthetic division. Remember, when you set this up, you are just writing the coefficients. You got to double check for placeholders, which we don't need in this case because this goes from cubed down to squared, down to x to the first, down to the plain old number. Bring down the 1 and start your synthetic. 5 times 1 is 5, gives me -6. 5 times -6 is -30, gives me 13. 5 times 13 is 65. Add and get 0, which just confirms the fact that 5 was one of the zeros. If they tell you a number is a 0 and you don't get a 0 here, double check your copying of the coefficients and double check that you did something silly with your arithmetic. Now, what does this mean? This is the depressed equation. If we fill in x squared minus 6x plus 13, the reason it drops down to x squared is because when you do synthetic division, whatever the power is of the problem, it drops down 1. So what we have to do now is solve this. This is a quadratic equation. X squared minus 6x plus 13 equals 0. One of the options is to see if this thing factors. Well, it doesn't factor. If it doesn't factor, your next best option is the quadratic formula. So negative b, negative of -6 is 6, plus or minus the square root of. I like to put that in parentheses. If that's a negative, put it in parentheses so your calculator does the right thing. Minus 4 times a, which is 1, times c, which is 13, all over 2 times a, which is 2 times 1. All of this part right here, you can enter directly in your calculator, and that's the reason I wanted you to put the negative in parentheses. So this is 6 plus or minus. If you type all that in the calculator, you have -16 right here, all over 2. Square root of -16 is 4i, all over 2. And this is where you can do what I call the triangle trick. If you look here, here, and here of those three coefficients, if there is a common factor for those three numbers, you can divide out the 2. 2 goes into 6 3 times, 2 goes into 4 twice, 2 goes into 2 once, and your answer will be 3 plus or minus 2i over 1, but there's no reason to write the 1. So the reason we were able to do this is we were given the fact that 5 was a 0. So 5 is kind of like the key that unlocks the equation for us, because once we get down to the quadratic equation, then we are able to solve. Every quadratic equation can be solved. Even if it doesn't factor, you can always use the quadratic formula on it. This problem is a little bit more involved than the last problem. First off, it asked me to list all possible rational zeros. If you have a coefficient of 1 in front of the highest power, then your possible rational zeros are just the factors of the back number, plus or minus thereof. So my possible rational zeros are 1, 3, 7, 21. So these are our possible rational zeros, plus or minus 1, 3, 7, 21. Those are the only numbers that could possibly be zeros for this polynomial. Unlike the last polynomial where you were given that 5 is one of the zeros, you have to come up with the first zero on your own. And one way to do this, and this is if your instructor does not allow calculators, one way to do this is to do synthetic division over and over again until you find a zero that works. So what I mean by that is, let's try 1. When I do my synthetic division here, 1 times 1 is 1, gives me 12. 1 times 12 is 12, gives me 43. 1 times 43 is 43. I add and I get 65. That tells me this doesn't work. If the zero that we have chosen here works, when I do my synthetic division, I will get 0 at the end of my synthetic division. That's what I mean when I say if it works. So negative 1 times 1 is negative 1, gives me 10. Negative 10 here gives me 21. And then negative 21 gives me 0. That verifies that negative 1 is one of the zeros. And then we can pick up, like we did with the last problem, with the depressed equation and go ahead and solve that equation. This is x squared plus 10x plus 21, and I'll go ahead and just put equals 0 just to save me a line. When you look at this quadratic equation, you have two choices. One of those choices is to factor or to use the quadratic formula. This factors, so I think that's faster, and that's what I'm going to do. X plus 7, x plus 3 equals 0. Use the zero products property, set each of those equal to 0. You can just look at those and say your other zeros are negative 7 and negative 3. So all rational zeros will be the negative 1 we found by doing trial and error with our candidates, and then the other 2 we got from the depressed equation. If this depressed equation did not factor, then my only way to go would have been to use the quadratic formula on it. Or if you just don't like to factor, use the quadratic formula. Now, that's one way to go, and that is the process if your instructor does not allow you to use a graphing calculator for this kind of problem. If we had tried negative 1 and I had not gotten 0 right here, then I'd have to try 3. And if that had not given me a 0, I'd have to try negative 3, etc., etc. A totally different way to go, and this is if your instructor allows the graphing calculator, would be for you to enter in your calculator this, y equals x cubed plus 11x squared plus 31x plus 21, and then hit graph and look at your graph. When you are asked to find the rational zeros, what you are also finding is the x-intercepts of the graph. That's the reason they're called zeros, because at the x-intercept, the y value is 0. That's an x-intercept. The y value is 0. So a way to do this with the graphing calculator is you type it in the calculator, you look at your graph, and you see where it crosses. Now, there's no guarantee it crosses at nice, neat integers, but in this one, it does. If you look at your calculator, you will see clearly it crosses at negative 1, negative 3, and negative 7. But to double check that, you could then go to second graph, which is actually your table menu, and take a look at the table. Find in your table where the y values are 0. You have a y value of 0 at x equals negative 1, at x equals negative 3, and x equals negative 7. So I didn't really need to do all of this work. By typing it in the calculator, I could find my zeros right from the calculator. That doesn't always work. Sometimes you find one number. It might be that it only crossed at the integer negative 1, and then we would do our synthetic division, with -1 on those coefficients and get the depressed equation. So what I'm saying is this: you have to come up with a 0 that works, a 0 that will unlock the door for you. In this problem back here, you were given the 0 of 5, and it unlocked the door because they told you it was a 0. Over here, we either had to find that initial 0 by doing synthetic division over and over and over again until we found a 0 that worked, or you can type it in your calculator and take a look at your graph. So this graph happened to cross at -1, -7, -3, and the calculator gave me all of that information, and I really didn't have to do synthetic division at all. That doesn't always happen. The third thing we have to do is factor the polynomial. Now, if I had been asked in the very beginning to factor this, look at the original function, if I had been asked to factor that, I would say, I can't factor that. I look at 4 terms, I think maybe I could factor by grouping, but if I factor by grouping, this is x squared plus, x plus 11 here, plus nothing to do down here. So this does not factor by grouping, which means I can't factor it directly. But what I can do is come in the back door, and that is this. If you know the zeros, you can write the factors very easily. If you have a 0 of -1, the factor is x plus 1. A 0 of -7 gives you a factor of x plus 7, and a factor of -3 gives you a factor of x plus 3, which is the appropriate factorization for this polynomial. It is not a factorization you would have come to directly. The only way to have gotten this is to have gone with the zeros. Pretend for a second that this was a positive 3, and that would have meant that this factor would have been x minus 3. But it's not. This is the correct factorization. So, a little more complicated problem here because we have fractions. It just says find all rational zeros. Well, if we're going to do it the non-calculator way, we have to come up with our possible rational zeros. But before we do that, we have to do something with this polynomial. First of all, it says p of x equals x cubed, etc. When you are solving this equation, you are finding rational zeros. The rational zeros are where the y equals 0. So I'm making an equation, 0 equals x cubed, etc. The reason I want to write it that way is we have fractions in this polynomial, fractions in this equation. We don't want fractions. So we're going to multiply everything by the common denominator, which is 3. 3 times 0 is 0. 3 times x cubed is 3x cubed. 3 times 1/3, the 3 cancels out. I just get x squared. The 3 cancels out here. I'll have 35x. And then 3 times 11 is 33. This polynomial is equivalent to the original polynomial, and I can solve this one. There are no fractions to deal with. So pretend this was the beginning. I see 4 terms. The first thing I think about is, hey, maybe factor by grouping, but this does not factor by grouping. So now I'm going to make a list of the possible rational zeros. I abbreviated PRZ, possible rational zeros. First off, the coefficients need to be integers. That's one reason I multiplied by 3. The other reason to multiply by 3 is nobody likes to deal with fractions. So multiplying by 3 gave me this polynomial, and now I can write the factors of the back number, 1, 3, 11, 33. I spread them out a bit on the top over the factors of the front number, which are 1 and 3. So separate that out. That looks like 13, 1 and 3. And now it is plus or minus, pairing these up, 1 over 1, 1 over 3. Then do 3, 3 over 1. 3 over 3, which is 1, which I already have. Then do 11 over 1, which is 11. 11 over 3 is 11/3. 33 over 1, which is 33. 33 over 3, which is 11, which I already have. This is my list of possible candidates. Now, I'm doing this from the standpoint of my instructor does not allow me to use a graphing calculator. So I would need to do synthetic division with 1, -1, 1/3, -1/3, 3, -3, until I find a 0 that unlocks the door for me. So I'll tell you, just to save a little bit of time, -1 is a 0 that works. So -1, 3, 1, -35, -33. Bring down the 3 and start your synthetic division. -1 times 3 is -3. Gives me -2. Multiply gives me positive 2. Negative 1 times negative 33 is positive 33. There's my 0, which verifies that negative 1 is a 0. Now, how do I know negative 1 is a 0? Because I've done this problem already. I tried 1, it didn't work. I tried negative 1, it did. So I'm down to my depressed equation, which is 3x squared minus 2x minus 33 equals 0. Believe it or not, this does factor 3x times x in the front, and it will be an 11 here, a negative 11, and a positive 3 right here, and that will give us the negative 2x in the middle when you FOIL that up. Set that equal to 0. Set each of these equal to 0 and solve. Gives me 11 thirds, which gives me, and also gives me negative 3 to go with the negative 1 that we started with. That is the non-graphing calculator way. You must make a list of the possible rational zeros and try synthetic division until you find one that gives you 0 in that position. Then you know you can complete this either by factoring or the quadratic formula. Now, if your instructor allows you to use the graphing calculator, you enter this function in the graph, take a look at it, and you will see that it crosses at negative 1 and it crosses at negative 3, and it crosses somewhere else, but it's a decimal. You can't really tell what that is. You can verify from the table function of your calculator that negative 1 and negative 3 will give you a y value of 0, so I know those are zeros. To find the other one, now pretend we haven't done all this work. We're letting the calculator tell us that these two are zeros. To find the other 0, I need to take either one of these and do synthetic division. Of course, I just did this synthetic division right here and get this depressed equation that you can finish either by factoring or with the quadratic formula. So the only difference in these two methods, the non-calculator way and the calculator way, is finding that initial 0. This way, it's a longer way. You have to find the initial 0 by doing synthetic division over and over and over again with these candidates till you find one that gives you 0 right there, and then you can complete it. This way, being allowed to use your graphing calculator, the graphing calculator will give you a starting point, negative 1, or I could have used negative 3. It doesn't matter.